Hey everyone, today we're going to pull back the curtain on something that feels kind of like magic, how a simple idea in your head becomes a real working computer program. We're going to follow that exact journey, from a basic thought all the way to an application on your screen.
I mean, really think about it. Every single app you use, every game you play, it all started with this question. It all began as just an idea. So how in the world does that happen? Let's break it down step by step.
All right, before a single line of code is written, something way more important has to happen. You gotta have a plan. It's so tempting to just jump in and start coding, but trust me, just like building a house, a great program needs a solid blueprint first.
I absolutely love this way of thinking about it. You wouldn't just start throwing random stuff in a pot and hope for a 5-star meal, would you? Of course not. It's the exact same thing with programming. Your plan is your recipe, telling you every single step to take so you get the result you actually want.
So how do we write this recipe? Well, one of the best ways is with something called pseudocode. And don't worry, it's not as technical as it sounds. Forget all the confusing symbols and syntax for a minute. This is just you writing out the program's logic in plain, simple English. It's all about the idea, not the computer language.
Okay, let's look at a super simple example. Our goal? Just add 3 numbers. The pseudocode makes it crystal clear. Step 1, start our total at 0. Then, we get our 3 numbers. Step 5 is where we do the actual math. And finally, step 6, show the answer. See, it's just a clear, logical recipe that anyone can understand. That's the real power of planning.
But hey, what if you're not a list person? What if you're more of a visual thinker? No problem, there's a planning tool for you too. Sometimes the best way to get your head around a program's flow is to literally draw a map of its journey.
And that map is called a flowchart. It has its own visual language, made up of these basic shapes. Ovals are for the start and end points. Parallelograms are for when you're getting data or showing a result. Rectangles are your workhorses. They're for doing stuff, like calculations. And maybe the most important one is the diamond. That's a decision, a fork in the road for your program.
So here's how those symbols look in action. You can see the program flows from the top down. It gets the marks, calculates the grade, and then it hits that diamond, the decision point. Is the grade less than 50? If the answer is yes, it follows one path and prints fail. If the answer is no, it follows the other path and prints pass. It's the whole program's logic right there in a picture.
Okay, so our plan is locked in. We've got a recipe. Now it's finally time to translate that recipe into a language the computer can work with. And for us, that language is going to be C++.
The Hello World program. Pretty much every single programmer on the planet starts right here. Its only job is to print those 2 little words on the screen. It looks so simple, right? But don't let that fool you. Every single symbol here has a purpose. Let's dig in and see what's actually going on.
Let's start at the very top. That line, #include IOStream, is what's called a preprocessor directive. The easiest way to think about it is like this. Before you start building something, you say, hey, I'm gonna need my toolbox for handling inputs and outputs. This line basically tells the program to go grab all the tools it needs for stuff like printing to the screen.
Next up, you see int main. This part is totally non-negotiable in C++. Every single program has to have a main function. It's the official starting line. When you run the program, the computer immediately looks for main and just starts doing whatever is inside those curly braces.
And here's the magic. Cout, which is short for character output, is the command that actually does the work. We are telling it to send the text "Hello World" out to the screen. That's it. This one little line is the C++ version of our plan to display a message. So we've written our instructions in C++. And that's great for us because we can read it, but here's the catch. The computer's brain, the processor, doesn't speak C++. It speaks machine code, which is just a bunch of ones and zeros. So, how do we bridge that gap?
This is the next giant leap in our whole journey. We have a simple text file with our C++ code. How on earth does that become an actual program? You know, a file you can double-click and just run.
Yeah, I know looking at this stuff, it can feel like pure chaos. It feels like it has to be some kind of magic, but I promise you it's not. It's actually a very logical, very organized, step-by-step translation process. This whole translation process has a name. It's called compilation. And this diagram here basically shows the assembly line. Our code starts at the preprocessor, which deals with those #include toolboxes. Then, the compiler translates our C++ into a language the computer understands better.
And finally, the linker puts all the pieces together into one final runnable program.
So, in a nutshell, you can think of the preprocessor, compiler, and linker as a team of expert translators. They take the code that we can read and write, and they turn it, step by step, into the raw instructions that the computer's hardware can actually understand and execute.
Now that might seem like a whole lot of steps, so you might be asking, why do programmers go through all this trouble? What makes C++ so important and so powerful that it's stuck around for all these years?
Well, for one thing, C++ has a long, proven history. It didn't just pop up yesterday. It started way back in the 80s, and it's been evolving and getting better for decades. That means it's been battle-tested in millions of projects, making it incredibly stable and reliable.
And all those years of evolution have given C++ some major advantages. For example, its object-oriented style lets developers build programs that model the real world in a really organized way. It also gives programmers direct, fine-tuned control over the computer's memory, which you absolutely need for high-performance stuff. All these features combined make it a real powerhouse.
When you get right down to it, C++ hits this perfect sweet spot. It gives programmers the low-level control they need to make things run incredibly fast, but it also has high-level features that make building huge, complex software actually manageable. That unique mix is why it's the engine behind everything from blockbuster video games to the operating system on your computer.
And that really brings our whole journey full circle, doesn't it? It all comes down to this simple, powerful idea. You have a problem, you make a logical plan, you write that plan down in a precise language like C++, and then you use tools to translate it for the machine. From idea to program. That's the whole game.
So as we finish up, I want to leave you with this thought. You now know the fundamental path from a human idea to a computer action. The only limit, really, is your imagination. So what problem would you want to solve? What would you want to build? What instructions would you give a computer?